is designed for you guys to review at home, especially the seasonal part of it. And you guys asked me a lot for previous test, so I uploaded a previous test with some annotations. Okay, so going through file one by one, we have the file that's called tutorial 2, but it's actually tutorial 3. Is the introduction to time series, and it's the file that we're going to see for about half of what our class is going to be. So you can see that it's the first, I believe the first, right? Yeah, the first file that we are going to see on our markdown. So you can see that extension .rmd. So before actually going into the time series stuff, I'm going to show you what's our markdown document. So an R markdown document is structured differently. Okay. So if you see our workshop, we have basically just lines of codes, and we have these separators that allows us to, separate stuff better, right? On an R markdown document, what you have is first you have this kind of table of contents thing. This is called a YAML header. What does YAML mean? Yet another markdown language. So it helps you structure the main attributes of your document, and it also helps you make a header once this gets exported. And what do I mean by export? So this is a document. This is a report that you can knit. So you can output into something. In this case, we're going to output an HTML. You can output different other things, mainly PDF. However, if you want to output a PDF, you need a LaTeX installation in your computer. I think Mini LaTeX is the one that's the lightest. I think it's only like 300 megs, whereas usually full-on LaTeX is like 18 gigs, something like that. What's LaTeX? LaTeX is software / language that allows you to write PDF documents in a very neatly fashion. Let me see if I have one in hand. I used to do these classes with LaTeX. There you go. Window Visual Studio. Okay, so this is LaTeX, and this is what I also use to write your exams. So you, just like R, you have a bunch of packages which give you functions. Then you have your title, author, date, etc. So, for example, I can here preview my PDF file. And you might have seen documents of this kind before. You guys, some of you may have known, some others didn't know how it was written. It's actually written with code. So this is almost what we've seen. I'll probably also upload this so you guys can have an idea of manual exercises. So it allows you to write neat things easily in terms of document representation and also equations. It's really, really useful for it to write equations. But enough of LaTeX. Let's go back to R. So on an R Markdown document, you have text parts and you have code parts. So a text parts, you basically structure like it would be LaTeX. However, it's much more easily. So you can basically treat it as if it was Word. Okay. Say, for example, in LaTeX over here, I wouldn't be able to do, yeah.
The screen is green, I think.
Green. Okay, let me reshare. What about now?
There's nothing.
So weird. Okay. Share.
You're not sharing, I think.
Okay, now it's not allowing me to click share. Let me relog. Hold on. Oh shit. All right, I'm back. So let's try now. What about now? Hello?
Yo no veo nada.
Yo sigo sin ver lo que estás compartiendo, Gonzalo.
So you guys do not see our studio at all?
No, sales tú.
No.
You're not
Sales
sharing.
tú, pero en freeze.
Ahora sí.
Ya está.
Okay, great. So weird team issues, because even after I closed down the test, there were still some phantom processes beneath. So I don't know. Where was I going with this? Yes. Our Markdown documents have to have text and have code. So for you to insert code, you have to insert a code chunk. This is a code chunk. How do you insert a code chunk? Control plus Alt plus I, or I, whatever you want to spell it like. With Control Alt and I, you can insert a code chunk. And notice that when I inserted the code chunk, it says R over here. This means that this code is getting run in R. What can you infer from that? That you can get code in different languages to run in R. So here you can write Python and run a Python code. Here you can run code in SQL. I believe there's also C++ capabilities and a lot more languages. So sometimes it's easy to mix and match. There are other chunk stuff that you guys can see on the R Markdown book that I've uploaded. The only other thing that I'm going to tell you about right now is a little bit of formatting and organization. So this setup doesn't mean anything. This is the name of the chunk. So whatever is after the language, it's the name of the chunk. It cannot have white spaces. It has to be just one string. Then this is a header, and if you wanted to make it smaller, you just add more hashtags. So this is a header level 5 or 6, level 6. Other things. This makes it bold. This makes it italic. Or even this makes it italic. There's some others you can cross some stuff. You can do upper cases, and that's all basic LaTeX formatting that's on the book, and you guys can read. Something else that we want to do before we start our thing? No. I'm going to knit this, and hopefully there are no errors. Okay, great. We're going to use the knitted document for now. Then we're going to go back to the code. Okay, so this is our output of our knitted document. Looks ordered. That's how I would describe it. So time series and ARMA models. Let's get to the point. So first, time series. What is time series? So you guys may have seen some time series stuff prior to this course. And you guys may have used some tools in order to describe time series. Probably the one that you've done the most similar to is apply statistics. I don't know if you saw anything on time series on econometrics 1, but you know the topics are regularly shifting, so you might. So time series. What is a time series? So a time series is a series of data points indexed or list or graphed in general. Okay. And what defines that it's a time series? That it has a time order. Okay. There is some kind of data point that tells you, some kind of variable that tells you which observations or which data points are connected to a specific date, and they are ordered. Okay. So most commonly, a time series is a sequence taken at a successive, equally spaced points in time, and hopefully, I desire you guys to always have an equally spaced point in time, because if not, you have to do some data cleaning. Thus, it is a sequence of discrete time data. Why discrete? Because you're not using continuous a continuous time variable. You're using it usually daily, monthly, yearly, or even more granular, by minute, by hours. Okay. You're not using like here it passed 1.6 seconds and then 1.666661 second. It's harder to work with that data. It's usually not very suggested that you do, but in some scientific fields you do have to work with that kind of data. So what kinds of time series can you have taken from real life examples? Say the weather forecast. What's the temperature going to be today, tomorrow, or in even just today? Now, in a couple hours, a little bit later. Monthly grocery sales, so numbers of sales, money, website traffic, stock market trend and predictions, and many more. So funny that we mentioned stock market. This is probably the one that we going to see the most, right? So here, let me just pop up the one that I have just open here. And let me change how it's represented so it's easier. Okay. So this is a time series. Okay, this is the the Nasdaq futures. My throat is kind of sore. Okay. These are the Nasdaq futures. You can see that this is a time series. Why? Because the series of data points that we have indexed to a date variable. All right. We can change the index. In this case, is days. Each data point is 1 day. We can change it to, I don't know, 30 minutes. Okay. And now each data point is 30 minutes. Except the last one, but each data point is 30 minutes. Yeah, let's go back to this and back to this. And let's go back to R. We're going to see a lot of those kinds of graphs, so it's not like you're going to be missing a lot right now. Actually, now that I think of it, we might go back in a second. So you can use that to make predictions and also to do some explanatory analysis. Okay. So time series analysis comprises of methods for analyzing time series data to extract meaningful statistics and other characteristics of the data. Okay. Now, what are some of them? You can say this time series exhibits a trend. It exhibits a seasonality component. It has cyclicality to it. So you can use those inference to make adjustments to your sales model, to make adjustments to your investment strategy. You can use it to do a campaign, okay, and so on. Time series forecasting is the use of a model to predict future values, and this is very important, based on previously observed values. Okay, every time that we're going to do time series forecasting, we're going to use the history to predict the future. In layman's language, forecasting is how time series will continue the same way in the future. Whilst there are many models, and we're going to see a bunch, that can be applied to time series, for the purpose of this vignette, so of this general example, we will focus on most commonly used models. And these are the two most basic ones, which are going to be the base where we construct every single thing forward. The first one is called autoregression or autoregressive models. For short, we're going to call it AR. And then we have moving average. Again, for short, we're going to call it MA. But before we start looking in these two types of models, we need to say something and define something. Stationarity. Okay, what is stationary and why do we care about it? Okay, so what do we care about it is, unless our time series is stationary, we cannot build a time series model. Well, to be more specific, we cannot build the basic time series models because they are not applicable to non-stationary time series. Now, after I've told you all of that, what is stationarity? So stationarity needs three things. So stationarity means that, first of all, a time series complies with all of these three. And we have degrees of stationarity, okay? You have weak stationarity and you have strong stationarity, okay? So three characteristics are, number one, the mean of the series should not be a function of time. It should be a constant, okay? So let's go, actually let's do a back-to-back. Let's go back to here, to our, let's go back to a line. Okay, so what can you tell me about this? Is the mean constant in time?
No, no es constante, o sea, varía por distintos periodos de tiempo.
Right. So if we're to do something, it's basically this, right? So there is a trend in our data, which gets the mean if we want to be, there's one mean, there's two means, there's 3, 4, etc. Okay. going to remove all of these annotations really good. So it's not mean stationary. Next, the variance of the series should not be a function of time. Oh, sorry that I've stopped the sharing. Is the variance of our time series regular in time? Is it? It's here. Do I have? I think it's over here. It's this one. No, this one. Okay. So here we have this range of variance. Over here, we have a much smaller one. Over here, we have this big one. Oh my bad. Over here we have, come on, this much bigger one. What's this one? So is the variance static in time, stationary in time?
No.
No, it's not, right? Next, is the covariance of the ith term and the I plus m or minus m term a function of time? What does that mean? And I think this is easier if I draw it. So basically, how can you quickly identify this? Is if you first have like some, okay, this is smooth as my line. I'm going to go to the Teams whiteboard. Okay, it's loading up. There you go. So first, we said that the mean, so the expected value of our variable has to not be.
Gonzalo,
Yeah.
I'm sorry, could you use another whiteboard? Because when we want to repeat the class, we can see the
Okay,
whiteboard.
sure.
Thank
course.
you.
How do I close this down? Stop percent. Okay, yeah. Yeah, let me open another one. Just 1 second, whiteboard. So if one uses the inherent one, you don't get to see it in the recording?
No, no se ve.
Well, it's a massive oversight by Teams.
Ni siquiera podemos ver el whiteboard después de la clase.
That sucks, really. Share. Windows. There we go. Since this is an independent window, you should be able to, right? Hello? Can you see it?
Yeah, thank you.
Okay, great. So, stationarity. We have 3 things that we've noted so far. First, the mean. Second, the variance. It really tries to smooth out my things. And third, the covariance. Okay, so mean. How can you see if the mean is actually stationary? You need to look for trends. Okay, if it goes up or if it goes down, then you know that it's not stationary. You need it to be generally flat. Okay. This is no. This is yes. Variance. If the disruptions are not generally the same, you do not have a good variance. You need it to be all smoothed out. And then covariance. How do you notice if the covariance is actually constant in time? You need to see for the jaggedness. Okay, so say this one might be like this. Come on. How do I tell this to not smooth me out? Maybe if I go to a softer one. Okay, the jaggedness. Yeah, if I do individual traces, it does it. Okay. If it's very, very constant movements and like very, very soft and long traces, that's then you have a non-constant in time covariance. Okay, it's like the spread of the deviations. Okay, you want it to be, again, very repeating in terms of intervals of the movements. Okay, let's go back to whatever it was, 3, I think. There you go. So was that clear, guys?
Gonzalo, ¿cuál era la que sí tenía covarianza? La de la derecha, ¿no?
So the ones on the left are time dependent on expectation, on variance, on covariance. And you want it to be non-time dependent, which are the ones on the right.
Ya, ¿y por qué no sería, o sea, y por qué no tendría dependencia con el tiempo la de la derecha?
On variance, on expectations, and on covariance. So on covariance is that you need it to be that the spread of time of deviation occurrences have to be kind of equally spaced. So let's make a bigger drawing of it. So if you have this, so each like something, it gets another change, right? Now it goes to this is a non-time covariance. This is a time dependent on covariance time series. Because over here, you have that the covariance is something, some number, and over here the covariance is completely different.
Ya, perfecto.
Remember that it's the covariance of an observation with the ones that are next to them. So each day, each year, each month has to be all the way around the same. Okay. All right. So I think with this we can return to our.
Gonzalo,
yeah.
What did you say it is important? Why is it important?
Why is it important? So we need these statistics frameworks for a time series to be stationary. Okay, that's the definition of stationarity. And why? It's because of math. And let's go to that. Okay. So why is because when these characteristics are not fulfilled, we do not have a clear idea of where that time series is going. And you can say, but basically every single time series in the world is not like that. And you're correct. And what do? We basically use some tools to clean the time series. So basically when we are doing forecasting, we're always forecasting a clean component of the time series and then adding all those things that we took away back. Okay. So a lot of time series get very much cleaned just with one or two cleaning components. Okay. So what do we use to stationarize the time series? The first one, it's detrending. Okay, we remove the trend component from the time series, usually using a logarithm. Okay. Can you imagine which one of the three does this fix?
I think that the trending helps with the variance to make
Yes.
it variance stationary.
Correct. So it hopefully it makes it very stationary, right? But it usually helps us with with number two. So variance of the time series should not be a function of time. And why? It's because when something is in logarithms, the change that it needs to be a relevant one in terms of movement needs to be way higher, right? So usually with medium-like spikes, it helps us move that down. Number two, differencing. So differencing, it allows us to usually remove one part of the non-stationarity, taking, so, all right, this is what you guys will probably use the most because we're working in a finance field. And why? Because think of what is return, but scaled differencing transformation. It is simply that. So it's very hard to predict prices. It's also very hard to predict returns, but it's less hard than prices. Okay, why? Because returns usually perceive as mean mean stationary. Okay. And why? Because they usually do not exhibit that line of constantly growing or constantly declining. Okay. In the long term, right? And that's why a lot of asset managers or strategies talk about mean reversion. Okay. They are not talking about price mean reversion. They are usually talking about return mean reversion. Okay, that actually has a second derivative that it goes to price, right? But in general, the main idea comes from return. Okay, so I have to sneeze. Okay, and the last one. Oh, I forgot to ask you. Which do you think is the one that difference fixes?
La primera en la media.
Yeah, the first one. And lastly, it's seasonality. seasonality can easily be incorporated into an ARMA model with the argument, and we're going to talk later about the arguments, but seasonality is basically, think of sales. Sales have cycles, okay? Usually, of course, it depends on the industry, right? But think of, I don't know, toys, okay? Toy sales. On toy sales, you probably have some spikes around, I don't know what's the name of it. Child's Day? Children's Day? Okay. And then you, throughout the world, have a spike during Christmas, okay? So in order to gather that into a model or clean that up, you always know that in Q4 or in December or even late November, you're always having an increase in your sales, and that repeats all throughout your time series. So you can model that out, okay, to clean up your time series and be able to forecast or explain better, right? That's seasonality. I've linked you some material on seasonality. Okay, we're not going to see it today, but it's going to be important, and I expect you guys to learn a little bit about it. So let's get to the models. Okay. So introduction to ARMA time series models. So ARMA basically, something went wrong. Okay. Can you guys hear me?
Sí, Gonzalo.
Yes, Gonzalo.
And can you guys see my screen?
Sí, Gonzalo.
Okay, great. So ARMA time series model. The first one that we're going to see, and probably the most common one, is autoregressive. Okay, so autoregressive model is probably the one that most people use. It shares a very, very, very similar interpretation to what you guys have already seen with OLS in Econometrics 1. Okay, how does it work? It works very, very similar to OLS. It is actually an OLS with different variables. Okay. So with OLS, you used to use y is equal to beta x plus your error. Okay. Over here, we're going to do exactly that, but your y is going to be your time series. Your x is going to be your lagged time series. And what do I mean by lagging? So by lagging, I mean that we're going to take it back one period, okay? So say the observation of today is explained by the observation of yesterday times a component plus an error, okay? So this is the most direct way to say we're going to explain today with information of yesterday. Okay. Here you can see the equation. Xt is equals to alpha xt minus 1 plus error on t. Okay. And again, this is an AR model, and because it's called AR, we're going to use these words to represent what a model is. And we are also going to use in a parenthesis, so AR parenthesis, what's the degree of the AR model? And what do I mean by degree? It means how many lags we're going to use in terms of our model. Say if we were using xt is equal to alpha 1, xt minus 1, alpha 2, xt minus 2, that would be an AR2 model. Once you keep adding more lags, you change what's on the parentheses. Okay. Right. So the equation above is an AR1. The numeral 1 denotes that the next instance is solely dependent on the previous instance. Again, if it were 2, we are going to be dependent on the first instance and the second one. Okay. The alpha is a coefficient which we seek as to minimize the error function. Just like OLS, you're going to get your coefficients and you're going to minimize the sum of squared errors, changing those coefficients. Okay. Notice that xt minus 1 is indeed linked to xt minus 2. And you can say, Gonzalo, how? Because this is an AR1 model, which means, let me rephrase that. This is a time series equation, which means that if we change anything in this t, it should hold still true. Let's replace t with t minus 1. So t over here is going to be t minus 1. Over here, t minus 1 turns into t minus 2, and error to minus 1. So we have that t minus 1 is linked to t minus 2. The same way, t minus 3 is linked to t minus 4, and so forth. Okay? Hence, any shock to xt will gradually fade off in the future. Why? Because this alpha, for this time series to be non-time mean variant dependent, it needs to be a value below what number?
Gonzalo, ¿podrías repetir la pregunta, por favor?
What's the range, the maximum value that alpha can take for this to comply with the first stationarity constraint? Nothing?
Should be 0.
Not 0. No. If it's 0, it's another kind of model we should use. We're going to talk about that later on. But nobody has a guess?
Capaz menor que 1 en valor absoluto, no sé.
Why?
O sea, yo creo que, tipo, si pones como que el alfa muy grande, podría ser que, no sé, que la media, como es un proceso autorregresivo, pueda fluctuar demasiado.
More than fluctuate, if you have a value that's greater than 1, then your time series is going to explode. And what do I mean by explode? It means, let's go back to the whiteboard. If you have a value that's 1 or greater, then you have your value, and that value, it grows by 1 point something, or let's say 2, and this value grows by 2, and this value grows by 2, and this value grows by 2, and you quickly go to oblivion, right? Here's alpha, where's that one? Okay. If your alpha is not greater than 1, this is a positive alpha, but it works the same if you have a negative one. Okay, so you were right in saying absolute term. Less than 1, then we have that you can have a number. It probably decreases a bit, then the error can pop it back up. It doesn't even matter, right? But you have something like this, right? So on this occasion, this is mean stationary, right? Let's go as far. Okay. So that's the reason that we need alpha to be less than or equals to, no, less than 1 in absolute terms. Okay.
Solo.
Yep.
Y es igual a 1 exacto.
If it's equal to 1, then you have something called unit root that we are going to go a lot more later on, because a lot of times series in finance look very unit rooty, but it brings on some new challenges. Okay, specifically because once you have a unit root, if you difference, or here, when you difference, usually you take the difference of the today with yesterday. You can also do a different spread, but usually it's just daily, okay? And if your time series is very, very similar today and yesterday, then what you have is that your any kind of influence that your time series will represent tomorrow is just based on the errors, so on new innovations. It is not based on a component that we are representing. So your new innovations are white noise. So it's harder to project where it might go. You just know that it will present a random behavior.
Okay, gracias.
So we need it to be less than 1, and for it to gradually fade off in the future any shock that we do today. Okay, so some characteristics. If alpha is equal to 0, then we have nothing that relates it to yesterday or to its history, and then it's just one noise, one white noise. If xt is autocorrelated, it is not stationary. What does autocorrelation means? So we talked about number 3. Okay, number 3 is called autocovariance. Okay, so we are doing the covariance of a term with the term before or even after. That's called autocovariance. Our autocovariance in this case should not be a function of time. If it is a function of time, and if there is autocorrelation, if there's autocovariance, usually there's autocorrelation, right? Because autocorrelation, or in general, correlation is just covariance divided by variance, right? So, if we have autocovariance, usually we have autocorrelation. Then it's not stationary, right? Large alpha lead to greater autocorrelation. Okay, why? Because if you have a greater value in alpha, it means that your history is definitely more linked to your present and to the future. Then negative values of alpha result in oscillatory time series. What does that mean? It means that you go from 1 point up top to 1 point at the bottom, to 1 point up top, to the bottom, and so forth. Okay, you change between positive and negatives. Moving average. So before moving to moving average, you get the general idea of AR. We'll do some examples in a few, but in general, you get it. That's hopefully a yes. Moving average. So you might have heard about moving averages before. That moving average can also be represented as a model. Now the thing is, it's not easy or even possible. Well, it's possible, but very hard. Model to run by hand. Okay. Because unlike what we did in AR, that it's an OLS, moving average estimations are run with numerical models. Okay. Sorry guys, they are painting in my house and there's a lot of dust building up. I'm getting allergies. So the simple moving average is a parsimonious time series that's used to account for very, very short autocorrelation. Okay. It does have a regression type form. And notice that we do not have the history of our data series present over here. It's just regressed on innovations, okay, so on errors, which are not actually observed, right? So weighted sum of them is called a moving average, all right? And again, just like the AR model, we have a denotation of them with parentheses, and this denotes how many innovations back in time we're looking at. So in this case, we're looking at one innovation back in time. This is an MA1 model. If we were to look at two innovations back in time, this would be an MA2 model. So once again, if the, in this case beta instead of alpha, is 0, then we have a white noise. Else, if it's not 0, we have autocorrelation, right? Because it depends on the previous error of it. Large values of beta lead to larger correlation. Of course, negative value, you have oscillatory time series. And then we're going to explain this one later with some math, okay? What's the difference between AR and MA? So first of all, AR, you're based on your relation to the past explaining the future or present. Over here, you have your innovations explain your present. Okay. Now, this is something that will help you once you go to this with pen and paper. That the correlation between the xt and the xt minus n term for n, so this one, so the spread in between your xt and the one that you're looking at, greater than the order of your MA is always 0, okay? And we're going to see it better with plots, okay? What does that mean? So it means that if you have an MA1 and you're looking at the second autocorrelation, that will be 0, okay? So with, no, let me just explain that just with plots later. Okay, however, the correlation of xt and xt minus n in AR models gradually declines, okay? And again, we're going to see this in a second. Why is this useful? Because this allows us to use something called autocorrelation plots, okay? Which are devised from the autocorrelation function and thus are called ACF, okay? All right. Let's go back to R, since this is more code than anything. There you go. Okay, so we're going to do some time series exploration before we move on to the review of Arima time series. Exploring data becomes most important in a time series model. Without this exploration, we will not know whether a time series is stationary or not. Okay, this is the first thing that we're always going to check for: stationarity. Okay, we'll use a data set called Air Passengers, which is a data set of flights in New York from 1949 to 1960 in a monthly format. Okay. Step one, let's load up the data. So we have this data in a package called TS. It's not loaded, but we have it. So we need to load up the data and check if we actually have a time series. So every single time that you want to look at your data, just look at it, right? This is how this object gets printed. You have your months, you have your years. Then there's a function called isTS that allows you to tell you if it's in a time series format or not. And you have true. Now TS is the very most basic time series object. Okay. After this came something called SU. After SU came something called XTS. Okay, and this is what most people use for their time series format. I usually do not use it. However, there are so many functions for analyzing XTS objects that I indirectly use it. And what do I mean by that? You guys know that I usually use tables. Okay, let's put a here slash. You guys know that I usually use tables because I like data frame time data. So some innovations have come with table time, and later we have tidy quant. This allows us to use any XTS function on a table. Okay. So again, because this is the first approach, I'm going to explain you with TS, which is the base our way of looking at things. But then we are going to move on to tidy quant. Okay. So yeah, it is a time series object. Next, let's do some data exploration. Okay, we printed out. We already know this. Let's use summary. So summary gives you the summary of your object. It depends on each type of object what data it gives you. In this case, it gives us data as if it were a numerical vector. So we get the general statistics of our underlying data. Now, the time part, the time component of a time series is called an index. Okay. So we can check when does it start. 1949 January. It ends on 1960 December. Okay. Time. This is our time index. Okay. Because it needs to be in a base 10 type of format, then we cannot have, let's say, 1949 0 or 1941 1, 1949 2, 3. No, it needs to be a one whole number. So the way that R is using this, it's going to split every single year into 12. And it's going to add 1 to the 12 to each one of them. And 1 to the 12 is 0.83. 0.083. Okay. Frequency, this will tell us that it's monthly. So 12 per Now, it is essential to analyze trends. So basically, we're going to see some analysis in order to check if our data is actually stationary or not. Okay. These are data plotted with the general TS plot, which is, again, the general plot of R. You guys are probably going to use ggplot with 2 G's. Even better, if you guys use eCharts, I will be surprised. Okay, so what can you guys tell me after all that we've talked about of this time series?
Parece que hay tendencia positiva, que la varianza está aumentando conforme aumenta el tiempo. Y
Yep.
con respecto al punto 3, es decir, no estoy seguro. Me parece que, no sé, creo que sí está como que en un patrón constante.
I would say that it's almost looks like it, but on the first one, you do have that innovations tended to happen less frequently, and then up to 1960, you have more frequent innovations. That's just by eye, right? But that's a good one. Thank you. Let's check the mean just to check the first one. You clearly have an upward trend, like you guys mentioned, right? So this time series is not stationary. It's not stationary mean. It's not stationary variance. It's probably could be stationary in correlation, but we still have to check. I think it's not. So autocorrelation, and this is something that we've talked a little bit before, but let's explain it. Okay, so autocorrelation is a very powerful tool for time series analysis. Okay, because processes with autocorrelation are more predictable than others. Why? Because it means that you're more dependent on your history, and this means that you're more predictable. When you're playing a game with somebody, let's say chess, let's say battleships, let's say Smash, you can see their moves, and if they exhibit a repeatable pattern, you can predict what they're going to do next, right? It's exactly the same. If they are more predictable, you can forecast it better. Total correlation chart, or autocorrelation function, ACF, is the function of the correlation with a time lag. So correlation of xt with xt2 minus 2, correlation with xt with xt minus 3, xt minus 4, and so forth. Okay. Autocorrelations or lag correlations are used to assess whether a time series is dependent on its past. For a time series x of length n, we consider the n1 pairs of observations one time unit apart. Okay, so xt with xt minus 1, xt minus 1 with xt minus 2, xt minus 3 with xt minus 4, and so forth. Okay, the first pair is x1, x2 with x1, the next one x3 with x2, and so forth. Each pair takes the form xt minus 1, whether t is the observation of the index, which we can vary from 2 to n in this case. So in this case, xt gets to t, 1 gets to t minus 1. Okay. The lag minus 1 autocorrelation of x can be estimated using the correlation of these two. Okay. Now, if the above doesn't make sense, there's a function. There's always a function, guys. That is called ACF. Okay. Every time that you do not know a function, check the help. Auto and cross covariance correlation function estimations. Okay. ACFs help us determine what type of series we have, whether it is a white noise, random walk, or autoregressive or moving average. Okay. Now ACF also can get us a plot of our ACF. This will be plotted with base R. There's also a GG ACF, by the way, if you guys are interested. So, what can we say about air passengers? Now, notice something. This might not be very intuitive in our index because we're using a TS object. Now, this first lag means 1 month, 2 months, 3 months, and notice that there are 12 upon reaching 1. This is 1 year. Okay.
Gonzalo.
Yep.
From the plot, indeed, we can see that the time series has autocorrelation.
It does have autocorrelation, yes. So that's the first important detail that we must know, right? We have here a confidence interval dotted in blue. We have positive autocorrelation on basically everything that we can see. Now, this basically exhibits something very easy tools to see, right? That there is a positive trend component, so we have autocorrelation on all of our plot. Second, there's also the seasonality component, right? That's something that we didn't talk about. That each, I think it looks like first or fourth quarter, we have spike in passengers. Okay, that also contaminates this a little bit. Okay, but we have positive autocorrelation, so that means that we could be able to forecast it, right? Let's feed an AR model. Okay, so we are going to use ARIMA. Okay, but so far we've talked about ARMA. What is ARIMA? So AR, again, autoregressive, MA, moving average. The I, it means how many iterations we're going through the time series. Okay. In this case, we're not going to use the I. Later on we will. What does that mean? I means that we are differencing our time series, okay? So remember, one of the ways to solve for stationarity is differencing your time series. If you put 1, it means that you are using your time series differentiate once. How do we do it? So we're building an AR1. So AR1 is the same as saying ARIMA and only filling the AR part, so the first one. The rest are going to be 0. Okay. So this is AR1, I0, MA0. Okay. And we're going to use a function called ARIMA. So ARIMA takes your object and the order that we just talked about. The rest are very useful arguments that currently we're not going to use. So the second one is seasonality. The third one, fourth one actually, no, third one, it means that if you want to include an external regressor, so say you wanted to regress by your previous lag and also inflation, you could put it over here, your inflation time series. Okay. And so forth, right? So we're going to run this and get the output. So this tells me what it run, the coefficients, the standard errors of my coefficients, and some statistics. Okay. So we have our intercept. Okay? We run it with an intercept by default because usually an AR works like an OLS model, right? So you have your, before your beta 1, you have your beta 0. Okay, so beta 0 plus alpha, in this case alpha, xt minus 1. Okay. Plus your errors, right? Errors. So, this is our model. How can you get more information? You put summary. Okay, not in the basic R function. Later, we're going to get more information with summary. Yeah, so you have your coefficients, and you have your standard errors. Now, notice your AR coefficient is very, very much close to 1, right? So we can get into problems with unit roots. So unit root, remember, it was when your coefficient was equal to 1. Okay. So in this case, we can see that it could be equal to 1. So check your standard error. Remember to get your, let's just look at this again. To get your confidence interval, you do your coefficient times plus your z value times your standard error, right? Now your z value, when you are using a 90% confidence interval, is very much closer to is like 1.965. Okay. So if you do this plus 1.96 your standard error, you're basically at 1. Okay, so 1 falls in between your confidence interval. So this could be a unit root time series. Okay, so also be aware of that when you're doing some explanatory analysis. So let's check our time series with what it estimated. Okay, so we are going to get our fit, which is basically our data minus the residuals. Let's plot it. It looks kind of the same. It gets it a little bit later than expected. So it's good, it's not great, right? Let's do an MA model. So instead of doing 101, 100, we're going to do 001. Again, kind of unit re. There's also something called our Akai indicator, which is it's a measure, also the log likelihood. It's a measure to compare models. Okay. Now should not compare, say, an AR model with an MA model, but it does give you an idea of what can explain your data better. So it's the equivalent of what you use on econometrics 1 with your R squared. Okay, it's how well your data gets explained. You want the one that's the lowest number for a guide. Okay. So with the Akaike and other information criterions like Bayesian information criterions and Hanaver information criterion, you always want the lowest one, right? They are explaining how well your data is getting represented, and you always want the one that has the least amount of variance to your data. Okay. MA. So we're going to fit our MA, print it, and represent it. Okay. This is our MA model. So it's not bad, right? But it's not explaining our trend, whereas the AR model was explaining our trend. So probably a combination of the two could help us explain it better, right? We're going to look into that in a second. Before looking into the function, is forecast. we can use the predict function to go and create a forecast with our current model. Okay. In between here, over the parentheses, it shows how many, again, how many periods we want to forecast. Okay. We want to predict. R is the first innovation. So first forecast, I mean. Our data ended at the end of 1961. So this is January of 1962. We're expecting 426 million passengers. Okay. You can also tell R how many periods you want to predict ahead. By default, it's just one, by the way. So here we have from January to October how many periods we wanted to forecast. Now, are these good predictions? Let's check. So here we have our forecast. Now, every single forecast comes with a standard error. So let's plot the range of values that it can have. It's not a very small range, right? So this might not be a good prediction, but what it has is that I think definitely your next values fall in between this area. Okay, so the standard errors are well represented, but not precise as we wanted to have. Okay, let's do the same for the MA model. This one not as good, right? So, how do you know which AR lag or MA lag to pick? We use the ACF plots. Okay, and also we check our information criterions. Okay, so in this case, our Kaike, or you can use the Bayesian information criterion, the Hanna-Bear one. You can pick. Okay. Now, one thing is that usually you must know your objective, right? A very, very good fit to your data might be good for explaining your data, but it might be too well fit to that specifically time window. And it might not be optimal for forecasting. Sometimes a lot of times, your best model to explain your data is not your best model to forecast your data. Okay, so you must define your objective. Do I want to explain this, or do I want to forecast this? Okay. Let's see our correlation in between our first model, the AR1, and the MA1 model. They have a very high correlation, right? So 96%. This is still not sufficient for them to produce very similar results, right? But in terms of explanation, they are basically explaining almost the same. Okay. What's the AIC on our AR model and the AIC of our MA model? 1400 and 1600. Which is the lowest one? Our AR. Which one yielded better results? Our AR. Not always it's going to be this way, but a difference of 200 is a very large difference. Okay. Any questions so far?
Gonzalo, una pregunta. Por ejemplo, en la parte que dices de RA y MA te salieron unos coeficientes. O sea, si yo quisiera ver si esos coeficientes, no sé, se me ocurre, son significativos o no, ¿qué podría ser en ese caso?
over here. So basically, what we did on the manually, if they pass 0, they are not significant. And this is what I always tell people when they look at a regression output. Always check your confidence intervals. In this case, you have that it passes 1, could be a unit root, but it definitely doesn't pass 0, right? Because if you take away, even with a 99% confidence interval, that you're going to take like 3.5 of this away, you're not going to pass 0. So it is significant. Our intercept is also significant.
Yeah, y no sería, porque creo que había como que una prueba con el p-valor, no sé, pero en este caso solamente es ver el número, no sé si tipo si está cercano a 1 o mayor que 0 significa que sí sería significativo, ¿no?
Let me show you this. What was our data set name? Air passengers? Okay, yeah, air passengers. Now, sometimes this doesn't help, but hopefully it does. Yeah, okay, it does. All right, here you have the usual output for exactly the same that we've done. Okay. Notice that both are significant, and for the AR one, by the way. And notice that this one actually rounds up the estimate to 1. That's a funny thing. Essentially perfect fit. Summary might be maybe unreliable. Okay, so also keep that aware.
Yeah, perfecto.
So if you were to look at it in OLS terms, your R squared and adjusted R squared are 1. This looks, to be honest, wrong, but because this also, yeah, this also looks different. It might be because we're using TS objects. That lag is not really helping. But anyways, it does have 3 stars. You can look at the p-value. I've never, I usually do not. When I get an estimation output, I just look at the estimate and the standard error. And I check, does it pass 0? Does it pass any other significant number that I'm aware of? In this case, 1. And that's what I check.
Yeah, perfecto. Gracias.
Awesome. Let's move on then.
Gonzalo,
Yep.
no entendí por qué cuando ploteaste le quitaste los residuos para el RFIT, o sea, para hallar el RFIT.
So that's their estimated value of our X.
Ah, yeah.
That's it. Yeah, just that. Nothing more fancy than it.
Gonzalo,
Yes.
¿cómo te puedes dar rápidamente si el modelo que has estimado es bueno para explicar tu data o para forecastear?
You look at graphically. You need to. So in terms of the objective, you need to test. Let's hopefully. No, I don't think we'll have time to get to that. But we are definitely going to look at that later. But you test. Let me go back to a board. Okay. Oh, so I can change colors. Okay, let's go to blue. So you have your data. Okay. You have your time series. All right. This will be a terrible time series to try to explain, by the way. But you use several parts of your time series. Okay. So with this part of your data, you're going to run some models. Okay, modeling. Again, this is for forecasting, guys. You run some models. With those models, you're going to create a forecast. Okay. And maybe there's one that fits better. Okay. Out of all of those, you pick the one with some forecasting accuracy methods. Test. With some forecasting accuracy methods, you pick the one that you want. So let's say that we pick this one, okay? Now, that's the one that you're going to use to continue the forecasting. If it was the better one in a certain period of forecasting, does it mean that it will be the best one in the future? No. Without any further information or context, it probably will be for our best alternative. Now, maybe you have some information about the next period. It's a slow growing period with mid to high inflation, and I have a model that did very well in the late 70s and early 80s. With that in mind, in a non-centralized, what's the word? When a lot of, in a not globalized environment, maybe instead of that one that worked in 2015 to 2017, maybe I don't use this one, even though it was very good for forecasting this period or the next few years. I maybe use this one because I have context. Okay. But without context, you're going to pick this one.
Me quedó más claro. Gracias, Gonzalo.
Awesome.
Gonzalo, ¿y eso que vimos del AIC es para ver lo de forecast o solo ver cómo, o sea, si explica bien el modelo?
The second one. So it's for explaining. For forecasting, we're going to look at different metrics. So let's quickly go back to our, and will we have time for this? Yeah, we should go quickly through this. Okay, yeah. So, since we don't have a lot of time, I'm going to go a little bit quicker. Now we're going to use our general language, which is Tideware, okay? We're going to simulate an ARMA 1.1, which is an AR1 and an MA1, which is the same as saying an ARIMA 1.01, okay? We are going to, in terms of our, this xt minus 1 is equal to 0.33 xt minus 1 plus 0.9 ET minus 1 plus your errors, right? Is what we're modeling. We're going to generate, let me previously delete everything else so we don't have clutter. We're going to generate this data. We're going to put it into a list. Okay. And we're going to use a function called arimasim. Okay. So we're going to set up our SID, 1,000 observations. We're going to use arimasim with the list that we created and 1,000 simulations. It's going to create our 1,000 simulations from an ARMA 1.1 model. Okay. After that, since this is a time series, we're going to use the function called core data, which will give us only the values. Okay. So index is the time part, core data are the values. And with that, we are going to create a table. So now we have a neat time series with our index and our values. Okay. Analysis. So let's look at it, of course. This is mean stationary time series, not covariance stationary time series, maybe variance stationary time series, could be. Let's look at the autocorrelation plot. This could easily be an AR1, maybe AR2. Okay. Now we know what it is. It's an AR11. It's an ARMA 1.1, but this could be an AR1. We look at the partial autocorrelation function, and it gets decreasing to 0. So this means that we could have an MA component over here. Okay, which one could it be? Could be 1, 2, 3, 4, 5, even 6, maybe. So we don't know, but we have an idea, and with that idea we can test, right? Let's, instead of an ARMA 1.1, let's create an ARMA 2.2. We have the air components, the AMA components, and we put it into the list. We can simulate that exactly what we did before. This comes from an ARMA 2.2. Let's look at it. Again, no. This definitely doesn't look covariance stationary. There's definitely some other correlation going on. We have some non-variance stationary, and probably the only one's mean stationary. Okay. Let's look at the autocorrelation plot. Now this looks very much like an MA function. I mean an AR function. Gets decreasing all the way to 0. Not that heavy on the AR part. Maybe 1, maybe 2, probably 2. So we have probably 2 components on the AR side of it. Again, you look at the autocorrelation for MA, partial autocorrelation for AR. Okay, both actually the autocorrelation gives you information about everything, but most clear bias towards one or the other. Okay. Let's use real data instead of just simulating. Let's see where this is living. Okay, should even do this. No. Okay. What about this? No. Never mind. Doesn't? I see. Okay. Let's just do this. You paste a string in R of a path, you gotta change the slashes.
O sea, no hay manera más eficiente. Yo
You
también
see
lo
it?
cambio mano por mano, uno por uno, pero no hay otra
You
manera
you
más.
you you, you can do Control F and do this one's to this one's
Como buscar
and
reemplazar.
replace all. Yeah.
Ok.
There's also an add-in. I think that I have it, but I never use it. Where are the add-ins? Here? No, this is. I'm going to show you this on later class, but add-ins over here. There's also an add-in that it auto converts it to one or the other. Come on. So this switches our markdown to more word-like. There you go. Where we here. Here we go. So we have JG dot. What is JG dot? Is what was it? Yeah, earnings about Johnson's and Johnson's. So we have quarterly earnings, quarterly data on Johnson and Johnson's earnings. Every single time, first thing that you're going to do, look at your data. So we have every single characteristics that we don't want over here, right? You have a mean, you have a trend, you have seasonality, you have variance, you have covariance. Everything at the same time. Oh, and something that I forgot to mention now that I think about it. I did mention that there were two types of stationarity, weak and strong, but we didn't talk about what's the difference. So everything that we've been talking, so at the moment, it's called weak stationarity because we're analyzing the first moment, so mean, and the second moment, correlation, covariance, and variance, to test for stationarity. Strong stationarity actually looks at all the moments up to infinity. So the third moment needs to be stationary. So skewedness. Fourth moment, kurtosis, needs to be stationary. Fifth moment, torque, needs to be stationary. And all the moments up to infinity, they need to be stationary. But that's hard to test, right? So that's why we use weak stationarity. Let's look at the autocorrelation plot. There's definitely some autocorrelation that we can use. There's definitely some MA components. There's definitely some AR components. Okay. Let's look at if there's unit root. So we can use the ADF test to let us check if there's a unit root. There is. I always forget which one is the alternative hypothesis. Okay, we have that this is stationary. This is not stationary, I mean. So we are accepting the null. This is not stationary. Okay. So what can we do? We've talked about different things that we can use. So first one, we know that it's not very stationary, so we're going to apply a log transformation. We know that it's not mean stationary, so we're going to apply a difference to that. So this is a diff log. And if you think about prices, this is not prices, but if you think about prices, or is it prices? Yes. Yes, it's not quarterly earnings, or is it? I forget. I'll tell you in a second. But if these were prices, we just would have gotten the return. Okay. So this is the diff log of Johnson & Johnson. Okay. No, this is the log of Johnson & Johnson. Oh, this is yeah, this is the diff log of Johnson & Johnson. Now that we apply our ACF to our diff log, it's much more it's much easier to see. So since we have a lot of spikes, we probably have a combination in between AR and MA, but it does fall down towards 0. So there's definitely MA components. if we look at the partial autocorrelation, then we have some AR components that we can look at it. Even up until like lag 4, we can have some things. So we can try different combinations. AR maybe 3, 4, 5. MA maybe 2, 3. How do I know 3, 4, 5? I see 3, 4, 5, even 2 maybe. Over here, MA maybe 2, maybe 3, maybe 4. Okay. How do we try different combos? So in general, you should use, so if you have context of your data, you can do some inference, right? Each 2 months, something happens, or in this case, each 4 quarters, something can happen. In this case, or even each quarter, something happens, right? So you can use that to construct your model. If you don't have an idea on what's going on, you can test a lot of them, and that's what we're going to do right now. So just so you know how does ARIMA work, and we've already seen, right? So in this case, we run an AR3 with an intercept, and we check the Akaike, okay? And again, you want the lowest one. You can extract that with Akaike, okay? I think there's also an AAC function. Yeah, there's an AAC function that you can also use. So what are we going to do? And this might be a little bit advanced into tidyverse. We're going to do a row-wise mutate, okay? So first we're going to use a function called crossing. So crossing, it basically generates an index, okay? An index of your individual combinations. So we're going to combine 0 up to 8 with 0 up to 8. How many combinations are these? 81 different combinations that we can do these two things for, okay? Why is it the 89, 81? Because we have 9 items here and 9 items here. 9 times 9 is 81. Okay, and we're going to test all of these models. So an ARMA 00, ARMA 01, ARMA 02, ARMA 03, AR 1, and so forth. Okay, for each one of the models, we are going to run an ARIMA. Okay, and we are going to have a third column of a variable that's going to not have values. Each one of them is going to be a new model. All right. So what this does, we're going to run a model with this AR, with this MA. And remember, mutate usually takes the whole variable. How are we going to use just the row? We're going to say row-wise before. So instead of looking vertically, you're going to work horizontally. This is not very much used, but for this application, it's perfect. Okay. After, we're going to, for each model, get out their AIC. And then we're going to order our data frame, our table, from lowest to highest AIC. It's going to take a while because it's running 81 models. Okay.
Gonzalo,
Yeah.
la razón por la que la diferencia es 0 y no la estás haciendo variar es porque ya hicimos la diferencia o...
Oh yeah, because we already did it. We're using the diff log. If we were using just log, we probably would test with 1 at the middle.
Okay, y solo yo sé que lo explicaste al inicio. La diferencia es más para la media y el log es
Yep.
más para los spikes de varianza que tiene la serie de tiempo, ¿no?
Correct.
Okay.
We have here our new table. Now notice the thing that I've told you in a second ago. You have here numbers, but here you have a list. In this case, each one of these spaces holds out a model. So if you go to models, you go to your model one and notice that it has objects inside of it by just the logo. Here we have a lot of models inside of it. And let's look at just one individually.
Gonzalo, una preguntita. Justo ahorita
Yep.
se me vino una duda. Cuando haces el A y C, queremos ver el menor, pero tiene que verse el menor en valor absoluto, ¿no? Porque ahorita he visto que hay un
No,
negativo
no, no,
demasiado.
no. It's the lowest generally. So if you have a negative value, that's even better, basically.
Ah, ya, o sea, tipo, si tenemos, no sé, un A y C de -1000, ese sería el mejor.
Mm-hmm.
Ah, ya, ya, perfecto, excelente.
Okay. So yeah, so we entered just the first one. So this is the one that has the lowest AIC. It has minus 151. If we look at the last one, which is 81, it has an AAC of minus 20. And this one is the AR00, ARMA 00, because it has just the intercept. Okay. So we have an AR3, MA2, which was inside our possibilities. So this is what we devised by just looking at the plots. And it was one of those. There is also a function that I would suggest you look. It will never serve as an answer to a question, okay, which is autoarima. Autoarima basically does this, and it tests a lot of different models, and it gives you the one with the lowest AIC. Okay, so in this case, it took an MA4. Now notice something. Our model is better than this one. Why? Because Autoarima didn't test a lot of them. It got one that it was content with, and it stopped. How can you know which models it did? You do trace equals true. So these are the models it tested. Okay. But again, this one is not something that serves as an answer to a question. Okay. All right, so let's extract our best model. Again, best model for explaining. Extract our best model. Let's get our residuals and let's put it into a data frame. Let's get them plotted into a histogram. Now, remember econometrics 1. How do you want your residuals to look?
Lo más mínimo.
Yeah. What else?
ID.
Yes. What else?
Homoceásticos también.
Mm-hmm.
In some cases, normal.
You want them to be normal. Yeah. So IID, normal, and mean 0. That's basically everything that you want to get. And also homostastic, right? How do you test if they are? Now we're going to add one layer to it. You want them to not be autocorrelated. Okay? Because if your residuals are autocorrelated, it means that there's something that you're not explaining with your model. How do you test a lot of autocorrelations? There's something called a Lumbox test. It tests basically an autocorrelation to the other. So we're going to test from 1 to 15 autocorrelations. Again, remember, as applied, we can use it. We are going to use an indirect function. We're taking our residuals, applying the box test, and getting the p-value. Okay. All of them greater than 0, greater than 0.05. So they are not autocorrelated. That's great for us, right? So luckily we made it in time. Okay. General guide for time series analysis for now. Okay. Number 1, always look at your data and identify unusual observations. With that, understand the pattern of your data. 2, now apply transformations or differencing to remove the trend and stabilize the variance. 3, test for stationarity, the one that we did, the ADF test. Okay. once we see unit root, we're going to look more into the ADF test, which is advanced decifula. But for now, use that to test for stationarity. Okay. If the series is not stationarity, go back to step 2. Okay. Then keep applying transformations and keep checking stuff. Number 4, plot the ACF and PACF to get an idea of what your AR and MA lags will be / ARIMA, right? 5, with your guesses, try different combinations of parameters and select the best models that fit your criteria. You can use AIC, you can use BIC, you can use AAC. Anyone works, okay? I like AAC, to be honest. Check your residuals and make sure that they look like noise, okay? Like white noise. Apply the Lume box test to make sure. There are more tests. So if you look at box test, you have more to be applied. Box peers in Lume box. And there's one other one. I think there's a Q test or something like that. But check if they are white noisy and they are not all correlated. Okay. And then if it's your objective, move on to forecasting. Okay. So this is where we've landed upon. You guys know how to analyze time series. You still do not know to do forecast analysis. You do know how to make basic forecasting with just predict. Okay. So probably our test is going to stop on time series analysis. If I pop something about forecasting, it's going to be very, very basic. Okay. So guys, any questions?
Gonzalo, una pregunta. ¿Cómo haces para que tu gráfico esté al lado y no se haga, o sea, no se plotee en el mismo R, en la misma consola? O sea, cuando corro,
In the console.
o sea, cuando corro el código, me sale en el mismo, o sea, debajo del
Oh, it
código.
pops up a window or below in the RMD. Okay, there's a. Oh, I stopped sharing. Let me go back. There's an option. I think it's in Tools and Global Options. R Markdown. Show output inline for all Markdown documents. You want to untick this one, and it should show into your console and plot window.
Ah, ya. Gracias.
No problem. Any question, guys?
Sí, solo una pregunta. Justo en el punto 2, no, en el punto 3 que dice Test for Stationarity, ahí tenemos que hacer sí o sí el Dickey Fuller, ¿no?
It's the most complete one. I would suggest you use that one.
Ya, ok, perfecto. Sí, y también una cosita, no me quedó claro cuando explicaste la significancia, o sea, tú más o menos cómo lo ves cuando quiere verse significativo. Creo que dijiste que no ves necesariamente el p-value, sino el valor, algo así.
So the p-value is good, and it gives you very good idea of it. And once you're publishing stuff, you should look at the p-value. But at least on my experience, I look at the confidence interval every single time. And most times the confidence interval is not there, right? So I look at the estimate and the standard error, and I do the confidence interval in my head. That's just for testing, right? Once you're doing rigorous work, do look at the p-value, do look at robust errors, and more stuff, so forth, right?
Ok, y en el caso, por ejemplo, esto de intervalo de confianza, ¿cuándo más o menos tú pensarías que efectivamente es significativo? ¿Cuando el intervalo es muy grande o muy chiquito?
No, that doesn't matter. What matters if it passes 0 or not.
Ah, ok, ok, perfecto, perfecto.
Gonzalo, para darte cuenta de que si tus residuos son como un ruido blanco, los ploteas así como tu serie de tiempo, ¿no?
You plot the distribution. If you plot the distribution, you can see if they are very close to 0, they are normal-like, then you know that they are white noisy. If they are not, you probably should look at your model and see if there's one better.
Entonces, lo que me fijo es que si se parece bastante a la distribución normal.
And center around 0.
Ya, listo, gracias.
No problem. Okay. If there are no further questions, guys, I will leave you to enjoy your Saturday and enjoy Easter, because we're not going to see each other for a while. If you have any doubt, hit me up. Look
Gonzalo.
at... Yeah, Junior.
Gonzalo, disculpa, lo que pasa es que llegué 5 minutos tarde. No sé si me podrías poner en asistencia, por favor. Creo que tengo falta para hoy.
Junior. Let me go back to... Sure. I'll put you down, don't worry.
Gracias, Gonzalo.
Okay, guys, so have a good one. Best of luck. Study. And I left you one previous exam, but I think that one has forecasting to it. It does have time series analysis, and it also has forecasting. So it does help you out. Okay. Look at it. I've given you the code and their output of one of the previous, I think it's 2020. And yeah, have a good one, guys. See ya. Bye.
Gracias,
Gracias.
Gonzalo.
Muchas
Cuídate.
gracias.
Chao, chao.
Gonzalo, gracias.
Gracias, Gonzalo.
Gracias, Gonzalo.